Have you ever wondered how the same water that freezes into ice can also boil into steam? This seemingly mystical transformation is a journey that water molecules embark on every day, right under our noses, and yet it remains a marvel of nature. Let's start at the very beginning. You see, water, like all matter, can exist in three states: solid, liquid, and gas. Each state is just a different costume that water molecules can wear, changing their appearance but not their essence. This ability to switch states is not unique to water, but is a fundamental characteristic of all matter. In its solid state, water takes the form of ice. The molecules are tightly packed together, vibrating but largely staying in place. They're like dancers in a tight formation, moving to the rhythm of the cold. Then we have water in its liquid state, the one we're most familiar with. Here, the molecules have more freedom to move around, sliding and gliding past each other. They're like children in a playground, running and laughing, free to roam, but staying within the boundaries. Finally, in its gaseous state, water becomes steam. The molecules have the most freedom here, moving rapidly and spreading out to fill all available space. They're like birds soaring in the sky, unbound and unrestricted. But how do water molecules transition from one state to another? What prompts them to change their dance, their playground games, their flight patterns? The answer lies in temperature. By raising or lowering the temperature, we can coax water molecules to switch states, to change their behavior, to embark on a journey of transformation. And what a journey it is! From the solid chill of ice to the liquid flow of water to the gaseous freedom of steam, water molecules experience it all. They dance, they play, they fly, they freeze, they flow, they vaporize, all in the span of a temperature change. So, let's embark on this intriguing journey of transformation that water molecules undergo. Imagine a water molecule comfortably floating in a liquid state, but then the temperature drops. As the air turns brisk and the warmth fades, our water molecule begins to feel the chill. It starts to slow down, moving less and less as the temperature continues to drop. But what exactly is happening here? Well, as the temperature decreases, the kinetic energy of the water molecule, that's the energy it has because of its motion, also decreases. It's just like when you feel lethargic on a cold winter day, wanting nothing more than to curl up in a warm blanket. Now, as our water molecule slows down, it starts to interact more closely with its neighbors. They begin to form a fixed, orderly pattern, like dancers finding their places on a stage. This is the moment when water starts to transition into a solid state, a process we commonly know as freezing. But there's a little twist to this tale. You see, water molecules are not just any molecules. They have a special kind of attraction called hydrogen bonding. It's a bit like the strong bond between best friends, always there, holding things together. In the case of water, hydrogen bonds are the invisible threads that pull the oxygen of one water molecule to the hydrogen of another. These bonds are responsible for the unique properties of water, including its ability to expand when it freezes. That's right, unlike most substances, water actually expands as it freezes. It's why ice floats on water. This happens because the hydrogen bonds arrange the water molecules into a spacious hexagonal pattern, creating a structure less dense than liquid water. As the temperature reaches 0 degrees Celsius, the freezing point of water, our water molecule and its companions are completely arranged in this fixed, crystalline structure. This is the point where water becomes ice, a solid state where molecules vibrate in place but don't move about freely. And just like that, our water molecule finds itself locked in a chilly ice crystal. As the temperature rises, our water molecule begins to feel a bit warmer. Welcome to the liquid state, the comfort zone of water, where its molecules are free to move around yet remain in close proximity. This is the state of water that we're most familiar with, and it's also the state that's most vital to life as we know it. Imagine our water molecule as a social butterfly at a lively party. It's not as tightly packed as it was in the solid state, where it was more like a wallflower stuck in one spot. No, in the liquid state, our water molecule has the freedom to mix and mingle, to move around, yet it still stays relatively close to its fellow molecules. This unique balance of freedom and closeness is what gives water its liquid properties. It's why water can flow, filling whatever container it's placed in, adapting to its surroundings. It's why it can seep into the ground, nourishing plant roots, or course through our bodies, carrying vital nutrients to our cells. The liquid state of water is vital in supporting life on Earth. It's the medium in which many biochemical reactions occur, the vehicle that transports nutrients and waste in and out of our cells, and the habitat for countless aquatic species. The interesting thing is, the liquid state of water is not just a property of temperature, but also of pressure. At sea level, water remains liquid between 0 and 100 degrees Celsius. But climb to the top of Mount Everest and water will boil at a much lower temperature due to the lower atmospheric pressure. So whether it's in our morning cup of coffee, the rivers flowing towards the ocean, or the blood coursing through our veins, the liquid state of water is everywhere, providing the conditions necessary for life to thrive. In this comfortable state, our water molecule can flow and adapt, but what if things get a little hotter? The temperature continues to rise and our water molecule starts to feel the heat. As we reach the boiling point, our humble water molecule finds itself in a state of unrest. The temperature is now a scorching 100 degrees Celsius, and the energy in the environment is palpable. The molecule, once content in its liquid state, now yearns for freedom. The increased heat blesses the water molecules with an abundance of kinetic energy. This energy propels the molecules, causing them to vibrate with such intensity that the bonds between them start to weaken. As the heat continues to rise, this energy intensifies, and the once close-knit molecules begin to drift apart. In this heated environment, a phenomenon known as vaporization begins. This is the transformative moment where our water molecule, fueled by the energy from the heat, breaks free from its liquid bonds and ascends into the air as a gas. Vaporization is a critical process for life on Earth. It plays a crucial role in the Earth's weather system and the water cycle. It is this process that allows the water in our oceans, lakes, and rivers to rise into the sky, forming clouds that will later return the water back to the Earth as rain. As the temperature continues to rise, the water molecules start to move faster and faster until finally they break free from their liquid state. They now enter the gaseous phase, becoming steam. This steam is not merely hot water, it's water in its most energetic state. Picture a bustling city at rush hour with everyone moving in different directions. That's what a steamy pot of boiling water looks like at the molecular level. Each molecule is free, moving rapidly in all directions, no longer bound by the close bonds of the liquid state. With a burst of energy, our water molecule has transformed into steam, completing its journey from ice to gas. This journey, from a solid state as ice, through a liquid state as water, and finally into a gaseous state as steam, showcases the incredible adaptability and versatility of water, a simple molecule that is the essence of life on Earth. So let's take a moment to reflect on this incredible journey. We've embarked on a fascinating exploration, witnessing the life cycle of water molecules as they transition from the freezing point to the boiling point. This journey, as mundane as it may seem, is a testament to the marvels of nature that often go unnoticed. We started in the depths of winter, where the water molecules were huddled together in a solid state, bound by strong hydrogen bonds. This is the freezing point, where water turns into ice, a state of rigidity and stillness. From there we moved into the comfort zone, the liquid state. Here the water molecules are in a state of flux, moving freely, yet still maintaining some semblance of order. This is where water is in its most common state, a state of balance. As we continued to heat things up, we arrived at a steaming climax, the boiling point. Here, the water molecules vibrate with such intensity that they break away from their liquid state and transform into gas, dispersing into the atmosphere. This transformative journey of water molecules is not merely a physical process, it's a symbolic representation of the resilience and adaptability of nature. It's a reminder that change is the only constant in life, whether it's the change of seasons, the change of states, or the change in our own lives. Transformation is inevitable. It's a journey that occurs every day in every corner of the world, from the polar ice caps to the steam rising from a hot cup of coffee. It's a journey that's been happening for billions of years, shaping our planet and life as we know it. The transformation of water molecules from freezing point to boiling point, though it may seem simple, is a complex and beautiful process. It's a testament to the intricate mechanisms of nature, the delicate balance that sustains life on Earth. And there you have it, the remarkable transformation of water molecules, a journey that happens every day right under our noses.